Imagine a sudden, uh, explosive release of energy, creating this localized pressure wave that just throws molten copper and shrapnel outward at the speed of sound.
Right, and we are talking about an instantaneous blast of temperatures reaching upwards of 35,000 degrees, which is, hotter than the surface of the sun.
Wait, hotter than the sun? That's terrifying.
Oh, absolutely. And this isn't some anomaly inside a military weapons testing facility. I mean, it's a very real, documented hazard lurking right behind the drywall of your office building.
Or even inside, like those metal cabinets sitting right outside your own home.
So welcome to the deep dive. Today, our mission is to decode the hidden language of the buildings you live and work in.
Yeah, the materials we've pulled together for you today are the actual foundational training manuals and rigorous study guides used to forge HVAC technicians. Right, the people who keep our modern, sealed-off world habitable. We're going to explore the fundamental physics of what HVAC really is, the raw electrical forces that power these massive systems, and the intense zero margin for error safety protocols required to simply survive working on them.
Because it really is life or death out there for these
It
techs.
really is. Okay, let's unpack this. And I think we should start with the acronym itself, because HVAC is, well, it's a lot more than just a metal box in the window blowing cold air.
Oh, for sure. Let's break that down. So the
All
H is for heating,
Yeah.
which is just the process of adding thermal energy to a space to, maintain comfort or protect the property from freezing.
Pretty straightforward.
Right. But the V stands for ventilation. And there's a huge misconception here that ventilation just means turning on a ceiling fan to move stagnant air around.
Like just creating a breeze in the room.
Exactly. But that's wrong. True ventilation is the deliberate introduction of outdoor air into a space. It's meant to dilute airborne contaminants, control odors, and manage indoor moisture levels.
So it's fundamentally about air quality and breathability, not just moving air.
Yeah, which leads directly into the AC part, air conditioning. People mistakenly use air conditioning as a synonym for just cooling.
Guilty as charged, honestly.
Most people do. But true air conditioning is the comprehensive treatment of air to simultaneously control its temperature, humidity, cleanliness, and distribution.
Wow. So cooling the air is just one fractional step of a much larger process.
Exactly. And finally, we have R for refrigeration.
Okay, this is where my entire understanding of temperature was turned upside down. The foundational rule in these training manuals is this massive paradigm shift. They literally say cold cannot be manufactured.
Yeah, it completely defies our daily sensory experience, right?
Totally.
When you drop ice cubes into a glass of water, your brain naturally assumes you are adding cold to the drink, but physics dictates that heat is a form of active energy. Cold doesn't actually exist as a physical property.
Which is just so hard to wrap your head around.
It is. Cold is purely the absence of heat energy. So an air conditioner or commercial refrigerator does not pump cold air into a room. It acts as like a thermal sponge.
A thermal sponge, I like that.
Yeah, it absorbs the heat energy from the indoor air into a chemical refrigerant, pumps that heat outside, and then just rejects it into the atmosphere.
So you were literally bailing heat out of a living room the exact same way you would bail water out of a sinking boat.
That's a great way to put it.
You aren't adding dry space, right? You were just aggressively removing the water.
Spot on. And understanding that bailing process requires looking at the profound nuances of human comfort. Because the thermostat sitting on your hallway wall is, it's actually giving you a wildly incomplete picture of your environment.
Really? How so?
Because a thermostat only measures sensible heat.
Okay, let me make sure I have this straight. Sensible heat is the thermal energy that causes a direct change in temperature, right? Like you can sense it on a thermometer.
Exactly. The mercury goes from 70 degrees to 75 degrees.
Right. But human comfort is dictated just as much by latent heat, isn't it?
Yes. Latent heat involves a phase change in a substance without an immediate temperature change.
Like what?
Think of water vapor in the air turning into liquid condensation on a freezing evaporator coil.
Okay, let's think about it this way for everyone listening. Imagine the air around you is a towel.
Oh, I see where you're going with this.
Yeah, so when you step outside in the summer and you start to sweat, a dry towel, meaning low humidity, wrings the moisture right off your skin.
Right, and that evaporation pulls heat away from your body, making you feel cooler.
Exactly. But if you step outside into, say, 90% humidity, the air is already a soaking wet towel. Your sweat has no way to evaporate. You just roast.
You're completely trapped in it.
Yeah, so the thermometer might only read 80 degrees, but the latent heat, all that hidden energy trapped in the water vapor makes it feel suffocating.
Which is why a properly functioning system has to act as a dehumidifier too. It forces that airborne moisture to condense on the coils. It basically wrings out the towel.
Because if it only lowered the temperature without removing the latent heat, you would just be sitting in a cold, clammy, miserable swamp.
Nobody wants that.
Yeah.
Furthermore, human comfort is heavily dictated by something called mean radiant temperature.
Oh, the winter window effect.
Yes, exactly.
You can be standing in a room where the air is perfectly heated to 74 degrees, but if you stand next to a large, poorly insulated pane of glass in January, you will feel this chill deep in your bones.
Because your body is literally radiating its own thermal energy across the room toward that freezing glass surface. The air between you and the window is warm, but the surrounding structural surfaces are just stealing your heat.
That's wild. So technicians really have to master manipulating heat transfer to combat all of this.
They do. Specifically, 3 types of heat transfer. There's conduction, which is direct physical contact, like heat passing through the copper tubing of the machine.
Right, making contact.
Then there's convection, which is using a fluid medium, like a high-speed blower fan pushing warm air through the ductwork.
And the third one?
Radiation, feeling heat through electromagnetic waves without any direct contact, like you just described with the window.
Okay, so if we connect this to the bigger picture, if we want to manipulate those 3 forces of nature on a massive scale, we need brute mechanical force.
Oh, absolutely. Bailing all that thermal energy out of a skyscraper doesn't happen by magic.
No, it requires immense power, which means that we have to dive into the atomic structure of the materials powering these machines.
Specifically, we have to look at the valence electron.
The star is the show.
Truly. In the atomic structure of elements, the valence electrons sit in the outermost shell, orbiting furthest away from the nucleus. And because of that extreme distance, the atom's magnetic grip on them is, well, it's incredibly weak.
Which makes certain materials like copper and aluminum the absolute backbone of the modern world. They are conductors, right?
Right. They only have a few valence electrons in that outer shell, and those electrons can easily be knocked loose and bumped to the neighboring atom.
And that cascading drift of free electrons down a copper wire is electricity.
Exactly. Insulators, on the other hand, like the rubber coating on your power cord, have full outer shells. Their electrons are locked down tight. They absolutely refuse to pass the energy along.
Good to know. But we also have static electricity, right? Like a stationary buildup of an unequal charge that discharges suddenly.
Yeah, like shuffling your socks on a carpet and touching a metal doorknob.
Just a sudden zap.
And that sudden, uncontrolled zap can instantly destroy a delicate microchip inside an air conditioning control board.
Oh, wow, really? Just a static shock.
Yep. But to physically spin a heavy steel blower motor, we require dynamic electricity. That's a continuous, highly controlled, relentless flow of electrons.
Okay, so the training materials use a classic water pipe analogy to explain dynamic electricity, but let's visualize this as a massive, bustling cargo train network instead.
Oh, I like that better.
Yeah, it gives a much better sense of the sheer industrial scale at play. So first, you have voltage, measured in volts. Voltage is the fleet of massive diesel locomotives. It is the raw pressure, the electrical potential difference, providing that immense push to get the cargo moving.
Okay, so then you have current, which is measured in amperes or amps. This is the actual flow rate.
The trains themselves.
Right, in our train network, current is a number of individual cargo cars passing a specific checkpoint on the tracks every single second. And just to put the scale into perspective, a single ampere represents roughly 6.24 times 10 to the 18th power electrons flowing past a point in 1 second.
Wait, so we are talking about billions of electrons.
Just for one single amp.
That is staggering. Okay, next is resistance, measured in ohms. This is the friction fighting the trains. It's the steepness of the mountain grade or like rust on the tracks.
Right, longer, thinner, or hotter wires naturally present more resistance, making it harder for the current to flow.
And finally, power, measured in watts. This is the actual tonnage of cargo successfully delivered to the destination. It's the useful work the electricity performs, like generating heat or spinning a fan blade.
And what's fascinating here is that these 4 quantities are inextricably bound together by Ohm's law and power formulas. Voltage equals current multiplied by resistance. Power equals voltage multiplied by current.
But that isn't just abstract math, is it?
Not at all. It is a vital diagnostic tool. Let's say a technician is looking at a blower motor where the internal bearings are failing. That mechanical friction translates directly into electrical resistance.
Okay.
According to Ohm's law, as resistance spikes, the motor draws more current to keep spinning.
Which means more trains on the track.
Exactly. More current generates extreme heat, which melts the wire insulation and eventually causes a catastrophic fire. The math literally predicts the failure before the smoke ever appears.
Wow. But the delivery method of that power matters just as much, right? Because batteries provide direct current DC, where the electron trains only ever travel in one single direction.
Right, but the heavy machinery in our buildings relies on alternating current, AC.
Because alternating current rhythmically reverses its direction of flow.
Yeah. In the United States, the standard utility frequency is 60 hertz. That means the current reverses direction and completes a full cycle 60 times every single second.
Which is just a staggering mechanical reality when you think about it. The massive steel rotor inside the utility company's generator, miles away from your house, has a physical magnet spinning past coils of wire.
Yep.
And to create 60 cycles a second, that massive rotor has to spin at 3,600 revolutions per minute. The physical, violent spinning of that generator is directly mathematically linked to the invisible pulsing of electrons in your wall outlet.
And the entire reason we rely on that pulsing alternating current is because it enables transformers.
Why do we need transformers?
Well, pushing massive electrical power across hundreds of miles of city infrastructure creates intense friction and heat loss. Utilities solve this by cranking the voltage up to incredibly high, dangerous pressures, which allows them to push the same power using a very tiny current, minimizing the heat.
But you can't feed high voltage transmission power directly into a residential air conditioner. It would explode.
Exactly, it has to be stepped down.
But how does a transformer actually do that without the wires touching? I mean, that sounds like magic.
It's the physics of electromagnetism. When alternating current pulses through the primary wire inside a transformer, it creates an invisible magnetic field that swells outward and collapses back in on itself 60 times a second.
Okay.
If you place the secondary wire right next to it, that pulsing, expanding magnetic field literally washes over the second wire, physically shoving the valence electrons in that new conductor without the two wires ever making physical contact.
That is unbelievable.
Isn't it? Depending on the coils, you elegantly step the high-voltage transmission lines down to a safe 120 volts for your home.
Wow. But here's where it gets really interesting. All that dynamic electrical energy is incredibly dangerous if it's just running wild, right?
Yeah.
It has to be contained within an electrical circuit.
Oh, absolutely. The sources outline the holy trinity of a functioning circuit. You must have a power source, a load to perform the work, and a complete unbroken path for the electrons to travel from the source through the load and back again.
And if the path is complete, it is a closed circuit and the machine comes to life.
Right. But if a wire snaps or a switch is flipped off, it becomes an open circuit. The path is broken and the flow of current instantly drops to zero.
But the nightmare scenario is the short circuit, isn't it?
Yes, it is. This happens when the current finds an unintended path that bypasses the load entirely.
So going back to our train analogy, imagine our cargo train bypassing the steep mountain delivery route and accidentally turning down a steep, frictionless downhill track.
Exactly. With virtually zero resistance to slow it down, the current spikes to massive, uncontrollable levels.
And the sheer thermal energy of billions of electrons surging without restriction will melt copper, vaporize insulation, and ignite fires in seconds.
This is precisely why fuses and circuit breakers are installed. They are intentional weak links designed to violently break the path and open the circuit the millisecond they detect that massive surge.
And how we intentionally arrange those loads and paths to prevent disaster is fascinating. Technicians work with two primary configurations, right? Series circuits and parallel circuits.
Yeah, in a series circuit, there is only one single path for the current to flow. Every electron must pass through every component in a single file line.
Let's visualize this as a theme park. A series circuit is like the single turnstile at the main entrance. Every single guest has to pass through that exact same gate.
Right.
If the turnstile jams, the entire park shuts down, nobody gets in. The total voltage, the energy of the crowd is shared across every obstacle they face in that single line.
Now contrast that with a parallel circuit, which is like the sprawling food court inside the park. There are multiple distinct vendor lines branching off the main walkway.
So every single vendor has full access to the main walkway's crowd.
Exactly. If the pizza stand closes its register, the burger stand keeps serving food completely uninterrupted.
And HVAC systems brilliantly exploit the specific behaviors of both circuit types to function safely.
They really do. The heavy lifters, like the massive compressor churning the refrigerant or the high-speed blower motor, those are wired in parallel.
So they each get their own dedicated branch off the main power line.
Yep. They receive the full unshared supply voltage, and they operate independently. But the delicate controls and safety sensors are wired in series.
Oh, I see.
Yeah, technicians will take a high-pressure switch, a thermal limit switch, and a low refrigerant sensor, and wire them all in one single continuous path connected to the main power relay.
So if a blower motor fails in the parallel circuit, the compressor might keep running, which would cause the system pressures to violently spike. But because the safety sensors are wired in series, acting as that single main turnstile, the moment the high-pressure switch detects the spike, it trips.
It jams the turnstile.
Yes, it breaks the single path for the control voltage, forcing the entire massive machine to instantly shut down before it destroys itself.
It is a brilliantly simple fail-safe architecture.
Yeah.
But, that brings us to the most sobering reality of these training manuals.
Yeah.
All of this engineering, controlling heat transfer, directing valence electrons, designing fail-safe circuits, isn't just about making a fan blade spin. It is quite literally about keeping the human technician alive.
Yeah, we opened this deep dive talking about the arc flash. The hazard sections of these materials are absolutely uncompromising.
They have to be. When people outside the trade think of electrical danger, they usually just think of getting a shock.
But shock is just the physical sensation of current passing through the human body, right?
Yes. The manuals heavily emphasize that human skin naturally has high electrical resistance when dry. But the moment a technician starts sweating on a summer roof or kneeling on a damp concrete floor, their body's resistance plummets.
They essentially become a walking sack of salt water, a near-perfect conductor.
Exactly. And a fraction of an amp flowing across the chest will disrupt the electrical rhythm of the heart. Electrocution means the shock was fatal.
And the arc flash demonstrates that you don't even need to touch a wire to be killed by it.
Right. If a tool drops across two high-voltage terminals, the electricity can actually ionize the air itself, turning the oxygen into a conductive plasma.
The current literally rips through the air, creating a blinding flash, vaporizing the metal tool instantly, and generating that concussive pressure wave we talked about.
It's terrifying.
So reading through these gruesome hazards, I have to ask if a technician needs to replace a burned-out wire inside a high-voltage commercial AC cabinet. Why can't they just walk over to the gray metal disconnect box on the wall, pull the heavy lever to the OFF position, and just confidently get to work?
Because the cardinal rule of electrical safety is that OFF is an illusion.
Wait, what do you mean an illusion?
A mechanical switch is just pieces of metal touching each other. Over years of use, the microscopic electrical arsking that happens every time the switch is thrown can physically melt and weld the internal contacts together.
Oh my God.
Yeah, so you might pull the plastic handle down to OFF, but inside the sealed box, the copper is fused solid. The power is still flowing.
That's horrifying.
Furthermore, opening a main breaker might kill the power feeding out to the machine. But the heavy utility wires feeding into the top of that breaker box are still completely live and utterly lethal.
So you can never, ever trust the switch.
Never. This is why the industry lives and dies by Olato lockout, tagout. A technician must identify every single potential energy source.
Not just the main electrical feed, right?
Right. Low voltage control wires, stored electrical energy sitting in capacitors, even the physical weight of a heavy fan blade or highly pressurized refrigerant gas.
They shut it all down, physically isolate it, and then apply a heavy steel padlock to the disconnects lever.
And they attach a high-visibility tag with their name and photo on it. Only the specific worker who placed that lock is legally allowed to possess the key and remove it.
But placing a padlock does not mean the wires are safe to touch, does it?
No, absolutely not. You must definitively prove the absence of voltage using a digital multimeter. And you cannot simply jab the metal probes into the machine, see a 0 on the digital screen, and start working.
Right. You must execute the live dead live testing sequence.
Exactly.
Let's unpack the psychology of this method because it perfectly illustrates how easily we trust our digital screens and how dangerous that trust can be.
For sure.
So, step 1, you take your multimeter and you test it on a known live circuit, like a standard wall outlet nearby. The screen lights up and reads 120 volts. You have just verified that your tool actually works. Then step 2, you take those probes and touch them to the dead circuit inside the AC unit you just locked out. The screen reads 0, so the machine is dead, right? Grab the wrench.
Well, this raises an important question. What if the battery inside your multimeter died the exact second you moved from the wall outlet to the machine?
Oh, wow.
Or what if the delicate copper wire inside the rubber probe lead snapped internally when you bent it? A broken meter will also show you a zero.
And if you trust that false zero, you are grabbing a live wire.
Exactly.
So you execute step 3. You take those probes back to the known live wall outlet and test it one more time.
Yes, and if the screen lights up with 120 volts again, you have successfully proven that your meter survived the entire process without breaking.
And therefore, the zero reading on the machine was genuine. Live, dead live. It completely eliminates the deadly variable of a broken tool.
And even after proving the machine is dead, technicians are still mandated to wear PPE, personal protective equipment.
And we aren't just talking about leatherwork gloves here.
No, technicians working near high voltage use thick, rubber-insulated gloves, but rubber degrades. The safety manuals mandate that before every single use, the technician must physically roll the glove up from the cuff, trapping air inside, and squeeze it to check for microscopic pinholes.
Because a hole the size of a needle is all the current needs to reach the skin and stop a heart.
Precisely. Which brings us to the brilliant engineering of GFCI's ground fault circuit interrupters.
Oh, these are the specialized outlets with the little test and reset buttons you see near sinks and wet areas, right?
Yes. They aren't just looking for massive short circuits. They're looking for tiny leaks. A standard circuit breaker in a basement electrical panel might require a massive 15-amp surge to trip, which protects the house's wiring from melting and starting a fire.
But a human heart can be stopped by a tiny fraction of an amp.
Right. So a GFCI is designed to protect the human, not the house.
It does this by constantly doing math, doesn't it? The GFCI counts the exact amount of current flowing out of the outlet on the hot wire, and it counts the exact amount of current returning to the outlet on the neutral wire.
Yep. If it detects even a 5 milliamp difference, meaning 5/1000ths of an amp is missing, it instantly assumes that missing current is leaking out of the system.
It assumes that missing current is flowing through the technician's chest and into the damp concrete floor.
And it physically trips the circuit open in a fraction of a second to save their life.
It is a profoundly sensitive safety net. But before we finish analyzing the hazards, we really must address the most pervasive myth in the field.
The idea that low voltage means no hazard.
Yes. Homeowners look at the tiny, thin wires running to their living room smart thermostat, carrying just 24 volts, and they treat it like a harmless toy battery. They think they can just splice it together with a kitchen knife.
Yeah, that's a huge mistake.
Yeah.
The manual states unequivocally that a 24-volt circuit can still spark violently.
Right. If it grounds out, it can create a dead short, instantly destroying the internal transformer and generating enough localized heat to absolutely start a structural fire inside the drywall.
Low voltage means a lower risk of lethal shock. It does not mean zero risk of disaster. Every single piece of copper wire is a loaded weapon until proven otherwise by a qualified, verified test.
So what does this all mean? We started by completely redefining air conditioning, learning that you can't magically manufacture cold. You can only aggressively bail thermal energy and humidity out of a room.
We zoomed all the way down to the atomic level to watch valence electrons power massive locomotives of electrical current.
And we explored how intricate theme park networks of series and parallel circuits direct that power with fail-safe precision.
And of course, we looked at the uncompromising psychological discipline of LO and live dead live testing that technicians rely on to survive, wrestling with this invisible force.
It means the modern comfort we so easily take for granted. You know, that blast of perfect air when you walk through the sliding glass doors is a highly controlled, incredibly potent harnessing of the laws of physics.
It is a remarkable triumph of engineering. But I do want to leave you with a final thought to ponder. Throughout this deep dive, we've seen how technicians can mathematically calculate voltage, current, and resistance to absolute perfection, right?
Right.
The electrical side of the system is entirely objective. It's governed by strict formulas. But the ultimate goal of all this perfect math is human comfort, which, as we discussed with mean irradiant temperature and latent heat, is highly subjective and biologically variable.
That's true. We all experience heat, humidity, and airflow differently.
Exactly. So even if we can engineer an electrical machine to perform flawlessly on paper, can a purely mathematical system ever truly guarantee a perfect environment for every subjective human in the room?
Wow, that is a fascinating paradox. The math is perfect, but the humans are decidedly not. Think about that the next time you walk into a room on a sweltering day, expecting it to be precisely 70 degrees, and you reach out to adjust that thermostat. We want to thank you for joining us on this deep dive. Stay curious.